Did everybody have a good weekend? Yeah? Yeah. Okay, good. So, last time we had finished off our section on testing and exceptions, and we had made some progress on the subject of motivating object-oriented programming. So, how many of you were here on Friday? Yeah, okay. Most of you, that's good. So, very briefly, objects are an extremely important concept in modern computing. Essentially, what you do is you take instructions in the form of functions, and you take data in the form of variables, you package them together so that you have data operating specifically on the data, you have functions which operate specifically on the data that they are relevant to and are packaged with the data that they are relevant to. This is the idea of classes and object-oriented programming. A class is very similar to a function because you write it down, but it doesn't actually get activated unless it has been invoked by another portion of the code, right? We can declare a function, but we have to also use it for it to actually run. In the same way, a class may be declared, but in order for an object to actually exist, it must be instantiated at some point. Obviously, you can have multiple objects of a particular class, and what was I going to say? There was one other thing. Yes. The one thing that sort of distinguishes a class from a function, insofar as we've studied functions, is the idea of persistence. Classes contain persistent data, whereas functions generally do not. If you want persistent data inside of a function, you have to make reference to some global variable within that function. With a class, you actually you have that data. It's still local to the object, right? But it gives you a new context in which to sit your variables, right? You don't have to put them in the global context. They can sit inside of the class's context. But with respect to all of the functions of the class, they kind of behave like global variables. Does that make sense? Yeah, good. Any questions before we start getting into it? Yes, sir.
So the same data you apply to all the functions?
Yeah, it's think of it like an octopus. Okay? The octopus has one brain and many tentacles. Right? The functions are the tentacles. The data is the brain. So the data is the head of the octopus is shared among many tentacles, and they all work together to perform the functions of an octopus. Sorry? Yeah, the octopus itself is the object, because it is the combination of the thinking parts, which is the data, and the doing parts, which is the tentacles. There you go. Any other questions? Good. So we're going to run through a number of examples today, and we'll explore various aspects of what it means to be a class, how classes are used, and various properties of classes. So, first and foremost, it is important to note, Python, being an object-oriented language, only contains objects. Every single thing that you have worked with in Python thus far has been either an object or some subcomponent of an object, right? So, for example, the number 27 is of class integer. That is to say that the numeric literal 27 is an object of the class integer. If we have a function declaration plus the type of this function is class function. Even functions are classes. Classes, in this manner, are what we call first-class objects, or first-class members of the language. You guys remember how we can pass functions in as arguments of functions? Guess what else we can pass in as arguments of functions? That's right, it's classes. We won't do that very much though, because it kind of cuts against the idea of methods, and it's kind of like, you know, let's just get the basics down first, but yeah. And of course, if we remember our person object, which we defined last time as class, obviously user-defined classes and objects are also classes and objects. Good.
So,
Question, yes?
so the class is basically like a box with different functions, like
Yeah.
is it a function or functions?
It's a little like, you really do have to bring in the idea of data as well, right? It's like functions with a shared pool of data, which all have a cohesive theme or operation, right? They all accomplish one goal, right? So, if you want like a more computer science oriented example, I've talked previously about the function call stack, right? Stacks in and of themselves can are preferred to be written as objects, right? The data actually contained in the stack, that would be the data component of that class. And the functions would be things like push and pop, and maybe a clear function, right? So the whole idea with respect to how you, the idea with implementing a stack as a class is that you take a data structure, right? It doesn't actually even matter what data structure you have as the underlying representation. That gets abstracted away. That's part of the abstraction. But you have a piece of data, right? You have some field of data. The functions restrict the means of access to that data. So the thing that makes a stack versus a list is the operations that you perform on it, right? It's not possible, for example, to do regular indexing on it. All you care about is pushing and popping, right? So by implementing it as a class, you can restrict the valid operations on that data to just pushing and popping, which gives you an actual implementation of a stack, right? Does that make sense?
Yeah. But does the order matter?
Does the order matter?
Like which function comes first?
Oh, the order. Not within the class, no. Yeah. The functions that exist inside, like the def init, def is married from last, you can do those in any order and it doesn't matter. Just like in a regular Python program, it doesn't matter in what order you declare the functions, right? Yeah. Make sense? Good. Any other questions? These are good questions. All right. So again, the thing that you want to think about with classes is you want to think of them as templates for objects. It's a template because this is what it has by default upon creation. The object is subject to modification after its creation. That's why it's only a template, right? It gives you the beginning, it gives you the start. And if you're wise, you don't pack too much into it after its creation. Like, it is possible to define new methods after you've instantiated the object in Python and instantiate new variables, and this is one of the reasons that objects in Python suck so bad, because it doesn't protect its own abstractions. But it's possible to be pretty loose with an object after its creation. But the class declaration itself is a template for the object's original creation. Inside of that template, you define the attributes, also known as properties, variables, members, and methods that are common among all instances of that class. So, as we're going to see, common to all instances is a very important idea, especially as it pertains to inheritance. Attributes of a class or an object are referenced using the dot notation. So if I have an object name and I want to access one of the attributes of that object, I put a dot and then I reference the name of that attribute. This attribute can be either a member variable or a method. It doesn't matter. If it's a method, then it requires parentheses in order to be executed, just like function. If you're just referring to the method as like a function that you're passing to another function, you don't require the parentheses. It's the parentheses that tell Python, I want this executed. Does that make sense? Good. So, here is an example of class point. In fact, I think I'm going to do this myself. We will create this one in a directory. This will be a live coding example. Yay! Boom. So, class point inherits from object, or nothing, it doesn't really matter. So, let me just put this, oh, yeah, I'll get the lights. Good?
Yeah.
Awesome. So, let me just put this here, put that there. Good. So, the first method that you should think about when creating a new class is the constructor. That is to say, the first thing that you should decide when you're writing a class, what data does this thing contain? So, assuming our purpose with this class is to write a class to represent points in two-dimensional Euclidean space. What do we need to know about points in Euclidean space? Yes, sir. Their coordinates, x and y. So, let's create that. Define initializer. Takes self. Self.x is equal to 0. Self.y is equal to 0. When we create a new point, it will be initialized as having, it will be located at the origin originally. Ha! Pun. Now, we can define a couple of methods. Some things that we can do with points in space. What's a thing that you can do with points in space? Okay. What was that? Somebody said it?
Translate them.
put in a translate method. Def, translate. Takes self. Takes dx and dy. Self.x plus equals dx. Self.y plus equals dy. Nice and simple. Every time the translate method is called upon an object of this class, the provided arguments dx and dy will be added to the relevant coordinate, thus translating that coordinate. Make sense? Another thing that you can do with points in Euclidean space is you can scale them relative to the origin. Scale them by some, scalar factor. Self.x times equals scalar. Self.y times equals scalar. If you want to be fancy, you can do like separate ones for the x and y, but we don't have to be fancy here. Yeah.
What does self.y mean exactly?
Very good question. So, the question is, what does self.y mean?
Or x?
Whichever, so this is a thing that's particular to Python, right? This is like an idiosyncrasy of the manner in which the specific programming language Python was developed. It is rare, to say the least, in other languages, but we are learning Python in this class extensively. The first argument of any method is self-referential. That is to say, it refers and names the object on which the method is being called. So you're giving a name to the method which is being called. It's not actually constrained to be self. That's just, it's conventional to call it self, right? You can actually use any name you want here, and as long as you use it consistently, everything works. So, give me 1 second. So, when we refer to self.x, self is the object on which the method is being called. X is the parameter of that class, right? So, in essence, up here in the initializer, when we create self.x and self.y, we are creating two parameters, x and y, which are bound to that object at the global level with respect to the methods of that object, but still local to the object, right? In that nice in-between space. We are creating it here, referencing it here. Self.x pops the reference outside of the local frame of the method itself and into the frame of the object itself, right? If we didn't have self here, x would be local to this function. Because we're using self here, it is local to the class. Does that make sense? Yeah.
So we don't need anymore to mention it when we're defining each scale inside of each function.
Oh, you mean like this? You don't need these lines repeated? Is that what you're asking?
No, like when we're defining the function, like in the bracket, like self-scholar, we don't need to put x and y anymore.
No.
We used to do.
Yeah, these define the inputs to the method, right? We haven't actually seen a method called yet, but we need to provide this argument to the method as we're using it like a function, right? So no, you don't have to provide these. To put x and y here would be to imply when I call scale, I am not only applying a scale factor to the point, I am providing new coordinates for x and y, which is kind of aside from the point of scaling an existing point. Does that make sense? Yeah. Yeah. You had a question?
Yeah, I was just asking a similar interpretation of how it's falling itself. I guess not.
No, the better way to think about it definitely is, it's much better to think of it as a scoping issue rather than a recursion issue. You can get recursion inside of classes. You can actually have recursion inside of classes in two ways. Methods can call themselves, just like functions can call themselves. And classes may contain instances of themselves. So, okay. Okay. We're going to do binary trees. Green chalk on a green chalkboard. My God. What in the blooming heck? Whose idea was that? Anyway, so we've talked about binary trees before, right? It's a structure. You've got nodes like that, right? Binary tree. In a binary tree, each node has at most 2 child nodes, right? We can define this as a recursive class, right? So if we say class, and maybe I want to do it on the computer. Do I want to do it on? Yeah, I'm going to do it on the computer. So if we define a binary tree class, right? Def init, not a lot, init, thank you. Like, I hope that this example illustrates to everybody how powerful classes actually are, all right? So, with our binary tree, let's imagine each one of those nodes held one number, right? Which is, about as simple as it gets. Self.value is equal to 0. Let's say we initialize it to 0, right? Self.left is equal to bin tree. Or actually, originally it'll be, oh geez, what did I do? There we go. We'll originally call it none. Self.right is originally called none. But what I'm going to do, essentially what we've defined with this class is we've defined a node which holds a value which has 2 references. At the moment, neither of them exist, right? So to this, we would add a method that allowed us to add a new node to the tree. But the node that we add follows this definition. So, for example, def add, so an easy way to like once we start getting into this, it's like we need to start making decisions. So one way that we can do it is let's say we wanted to add a number to an existing tree, right? What you require is some mechanism for deciding where to put the new node. One of the simplest ways to do this, which actually creates an object called a binary search tree, is take the number you want to add, compare it to the existing number, or the number of the node that you're on. If it's less, go down one branch. If it's greater, go down the other. And then recursively follow that same algorithm until you hit a point where there's no more nodes, at which point you add the new one. Right? Question?
Why did you add self after the bracket?
Oh, because I made a mistake. Yeah, sorry. So add number. Takes self and the value, or say new value. Right? I might be stepping on the tutorial's toes. They might be doing this in tutorial at some point with you guys as well. But anyway. First we compare it to the existing value, right? If new val is greater than or equal to self dot value, we do one thing, else we do something else. So let's say we do it greater than down the left, which I know for you guys is right because you're in bed. So if self dot left is equal to none, we do something, else we do something else. So if the node doesn't exist, we want to create it, right? And while we're at it, let's just add an initializing value to the constructor. There. Now we can when we create the new node, we can add this as a parameter to the constructor, right? So if self.left is equal to none, self.left is equal to bin tree new val. So we construct a new node on the left branch if there's no node there already. If there is a node there already, we follow that branch. So we recursively call self.left dot add number new val. Copy this boy, paste her up. This is an approved use of copy paste. Right, right, right. And that is actually all you need. This constructs a binary tree. So this is using a recursive algorithm to construct a recursive data structure using a recursive class. Like, I know that recursion was kind of like, I don't know why I'm learning this, you know, when you guys were doing it like a month ago or so, or whatever it was. And?
Assignment 5.
Assignment 5, well, a couple of weeks ago then. I know that recursion probably seemed like, you know, not a terribly interesting or useful thing to do, but when you start actually dealing with real problems and real data structures, you'll find that recursive formulations to data structures are actually quite common. It's common because this is a short amount of code that generates a hell of a data structure, right? Binary search trees are called search trees for a reason. If they're properly, if they're constructed slightly more intelligently than this with some balancing, a binary search tree is a static data structure which yields the same search speed as the binary search algorithm, right? You can get at you can test this thing to see if something's in it in logarithmic time, right? Make sense? Okay, good. These are very good questions.
So, can I ask a question?
Yes.
So basically the self, kindly what the self does to the parameter is like make it global, right? It's a similar concept.
It's similar to the concept of giving it globality, if that's a word, but constrained to the class. It's still like local to the object, but it's local to all of the methods of that object, right? So it's like an in-between layer of the.
It's only global but within the class.
Yes. Good. Excellent. Yeah. So, There's one other thing which may be of interest here. Returning to our point example, what's one other thing which is of interest with respect to points? Is this?
I was just going to ask if we can see the binary search hash.
Oh, yeah, let me finish this and then we'll do that, okay? Yeah. Another thing which may be of importance when you have more than one point is determining distance between 2 points. What formula relates us? The magnitude between the distance between 2 points. How do we get that in Euclidean space? Well-known formula?
Like the rearrangement of the Pythagorean Theorem.
Yep, Pythagorean Theorem. So, but this should be interesting because this is going to be an example of a method which must accept 2 objects, right? So, define distance takes self and other. In the same way that self is conventional for the self-referential argument of methods, other is traditional when you have 2 of the same type of object that you want to feed into one method. You do self and other. That's just like again, there's nothing syntactically that's constraining you to do that. It's more conventional, right? So, return x times x plus y times, I guess we can do it with exponents, why not? X squared plus y squared to the power of 0.5. Bing, bang, boom. Good. So, I'd just like to demonstrate how this is now used. It's because we've defined classes, but we have not created objects as of yet. So, let's say A is a point, B is a point, A dot x is equal to 7, A dot y is equal to 3, B dot x is equal to -2, B dot y is equal to 9. Print A dot x, print A dot y, see what things look like. So you can see that things are stored reliably. Let's A dot translate -2, -2. You can see, oh, well, maybe you can't. You can see we start off with 7, 3, we end up with 5, 1. Very, very simple. And if we wanted to, we could say print A dot distance B, and we get x is not defined. Yeah, I did an incorrect thing. Self dot x minus other dot x. Yeah, I got too enthused. I got carried away. Self dot y minus other dot y. Sorry about that, folks. Yeah. In order to actually take the distance between 2 points, you have to take the coordinates and subtract one from the other. So, yep. How embarrassing. Anyway, so the distance between those 2 points is 10.63. Math. Make sense? Good. So, now let's do that thing where we take a look at how the binary tree works. So, in order for a binary search tree to actually be a binary search tree, it has to have a search function, right? Because of the manner in which it's been constructed, we can the thing that makes a binary search tree work is we always know which branch we need to go down to find the thing we're looking for, right? And that's only correct because of the construction of the data structure, right? Because the construction of the data structure has been constrained such that it has been, nodes on the left branch are always greater than or equal to, and nodes on the right are always less than. We can use that information to do a more efficient search of the tree. So, def search self and searching S, right? If S is greater than or equal, well, if S is equal to self.value, return true. If elif x is greater than self.value, we do one thing, otherwise we do another. If self.left is equal to none, we return false. Because we're looking for the value on the left node. If the left node doesn't exist, then neither does the value there, so we return false. Otherwise, we repeat the same operation on whatever's in that left node. So self.left dot search for S, bing bang boom. You may notice that this is shockingly similar to the function which constructed this darn thing. For the right node, it is precisely and exactly symmetric. Make sense? Good. And, self dot depth counter. Just going to put that in there so that we can see how deep the thing actually is, right? So let's generate some numbers here. Right? Question?
Is it possible to scroll down a little bit so I can see?
Oh, yeah, sorry. Like that?
Yeah, whatever, it's just so I can see the end of the search function.
Yeah, that's the end. So, question?
Use X instead of S. Search with the final search.
I used X and, oh, I didn't use X instead of S. Thank you. Ha 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 ha. Silly me. There we go. So, let's say 1, 2, 3, 4, 5, 6. That conforms to that pattern. Wait, I did it the wrong way around. Because left is higher in this one. Do it backwards. 6, 5, 4, 3, 2, 1. So, we're going to have to add them in the right order though, especially when we get down here. So we'll add 3, then 5, then 4. If we add 4 first, then we'll just get things lined up down that way. So that's the thing about a binary tree, a binary search tree, is it's somewhat vulnerable to the manner in which it's been constructed, which is why we have balancing algorithms, but we're not going to get into balancing algorithms. It's just, So, let's say we have, what's a species of tree?
Birch.
Birch. Birch is equal to bin tree with an initial value of 3. Birch.add number. We'll add 5. Four, 6, 2, 1. Right? It can be somewhat tricky visualizing these things, but just trust me, it'll look like that. So birch dot, so depth counter is 0. We'll just reset that, even though it doesn't need to be, because we're about to perform the search. So I'm going to make it so that every time it recurses the search function, it adds 1 to that counter, so we can measure the depth at which the node we're looking for is found. So, because that will just be a quick verification that the thing is actually structured the way that we say it is. So, birch.search, rhymes. Let's look for 2. That's 2. Print birch.depth counter. 1. All right. Let's see here. What's going on here? Is it even working? Let's see if it's even working. None. Oh. How's it going to get the result if you're not returning it? Toy bag. So true, but the counter isn't working. Must be making a mistake somewhere. Oh, I know what the yeah. Okay. It's going to have to be a global. So, here's the mistake I made, right? By binding depth counter to the class, this is actually a very informative mistake. By binding binding the depth counter to self, what I've done, in essence, is I've given each one of these nodes its own depth counter, right? So when it's returning the depth counter at the top of the node, it's not counting all the rest of them, right? So that's why it's not working. So in essence, we'll have to just make it global. work. There we go. So 1 is at a depth of 3. 1, 2, 3. Two is at a depth of 2. 1, 2. Right? If I were to go for depth of 3. If I were to go for Jehoshaphat, does not exist, or it's a type error because I'm comparing strings. I just wanted to do something silly, but then I got an error. So when you're looking for a number that doesn't exist in a binary tree, you have to assume that you're going to have the worst case scenario. Like in theory, you could go down this branch, down that branch, and then find nothing, and then exit at that point. But you have to assume that you'll hit the end of the tree. So you're using your worst case search time. Just like any other search that you perform. If you hit this one, you only have to go back far, right? So we're interested in all cases in the worst case runtime. But yeah, so that's binary trees. Is that cool? Yeah. Any other questions before we? Yes, sir.
Do you mind just scrolling up to the top where you can find this little?
Yeah. Any other questions? Good. All right. Anyway. So. Methods are called using dot notation. The first parameter, named self by convention, is bound to the object of call. So p.move, or translate, 1.1, is the same thing as point.move p11. So this is kind of a little bit of a technical point. But essentially, this is the origin of the this is where self actually comes into it. So we've got two different ways of writing this. Right? Point dot move P1, 2. These are the same statements, written two different ways. If you'll notice, the way that it's defined inside of the class itself is def move self dx dy. Not in cursive, but you know. So, with this style of declaration, it's obvious and clear how things line up, right? P binds to self, 1 binds to dx, 2 binds to dy. One-to-one translation. This guy here means that you are referring to the class declaration rather than an instance of that class. You're referencing point, not an object of type point. Right? In this case, it's an abbreviation of this one. Right? You assume that because P is of type point already, it has the move class, so you don't have to refer to the class. Right? This guy binds to self. This guy binds to the second parameter. This guy binds to the third parameter. Makes sense? This is like this may seem academic, but it's actually kind of useful, as we shall find out when we start looking at what's it called? Inheritance. That type of construction is actually very useful for referencing the methods of different inherited classes without needing an object to refer to. Thank you very much for your time today. I'll see you on Wednesday.